Dear students, welcome back to the multiple integral session. Today is the third session on multiple integrals. Let me refresh whatever we taught in the previous two sessions. In the session 2, we had a discussion on the three types of regions, mainly type 1 region, which is where all the limits are constants. The region in the xy plane was the rectangular region. We did the integration by using the iterative integrals, first with respect to x, then with respect to y. That was the first type region. And the second type region was whenever the y limits are functions of x, they are y is equal to, you can see the picture, g1x and y is equal to g2x, and also the x limits are constants, a and b are the constants. So that double integral was integrated first with respect to y using the y limits y equal to g1 to g2x. So after the integration with respect to y, that became the function of x, then which is integrated with respect to x using the limits x equal to a, x equal to b, that gives the value of the double integral. This is of the type 2 region. So type 2 region is mainly the one of the limits are functions of x, which you consider them as y limits. Similarly, the other one, type 3 region. Here x limits are functions of y. One of the limits out of two set of limits, one of the limits which are functions of y, you consider them as x limits, and the other constant limits are taken as the y limits. So in such integration, first integrated with respect to x using the x limits, it becomes the function of y. We have seen already that becomes the function of y. Then integrating with respect to y, that gives the value of the double integral. And also, if the integration of the constant function over the region R, that gives the area of that particular region R. Suppose the function value is 1, that is constant. If f of xy is 1, then the double integral over the region R dx dy gives the area of that region. Your region is a rectangle, you will get the area of a rectangular region. If your region is bounded by the curves, that gives the area of that particular region. So is it the area? The question is, mathematically, the calculation wise, it is the area into, as per we had a discussion, all the double integrals, the values, they are giving the volume under the surface. Here the surface is 1, z is equal to 1 or fx is equal to 1. So what we do is, the area is multiplied by the height of the rectangular box. So area into 1, it gives the same, dx into dy. That is why it is the area of the region R, where R may be any of the type. Type 1, when all the limits are constants, so that gives the area of the rectangular region. It may be type 2 or type 3. Type 2 and type 3, you know that they are, one of the limits are functions of x or functions of y. So that area gives the double integral if fxy is equal to 1. Now we discussed in earlier classes, whenever the limits of integration are given directly, x limits and y limits are given directly, but in many problems we evaluate the double integral of some function over the region R. R is bounded by some curves. So we need to identify what are the x limits, what are the y limits. You can convert this using these two curves. You find out the x limits are constants and y limits already given 2x square and 1 plus x square. So what are the x limits you calculate? That becomes the type 2 region. One can also do type 3 in this problem. So you consider type 2 here. There are two parabolas, y is equal to 2x square and y is equal to 1 plus x square. To find out where they are intersecting, solving these two or plotting these two on the graph paper, you can easily identify where the x boundary, x limits are. So solving them, So, y is equal to 2x square, substituting y value here. So, 2x square is equal to 1 plus x square, simplifying that. So, 2x square minus x square, that is x square is equal to 1, that simplifies to x square is equal to 1. So, x is equal to, you can easily write plus or minus 1. So, the x range is minus 1 to plus 1. So, the reason R is of type 2 here. Why it is type 2? The x limits are constants. So, minus 1 to plus 1, and y limits are functions of x. Which are 2x square, that is one parabola, 1 plus x square is another parabola. So, in this picture you can see both the equations. Y is equal to 2x square, it is a parabola, everyone knows that. It is passing through the origin 2x square. This is the lower limit, you consider lower curve, and the upper limit you consider the upper curve. This is in the y direction, y axis. So, y is equal to 1 plus x square. It is also a parabola not passing through the origin. So, it cuts the y axis at 1, means when x equal to 0, the y is 1 here. When x equal to 0, y is 1. In this parabola, when x equal to 0, y is 0. That is why it passed through the origin. It passed through 0, 1 point, x equal to 0, y equal to 1. So, this is our reason. So, in this reason, we identified x is minimum minus 1, they are intersecting at minus 1 and plus 1. So, these are the x limits, and y limits are given, y equal to 2x square, 1 plus x square. Now, integrating this, since the lower boundary is y equal to 2x square and upper boundary is y equal to 1 plus x square. Now, integrating the double integral over the region R, it is given x plus 2y into dA, dA is dx dy. Now, it is written here. So, whenever y limits are function of x, first we do the inner integration, that is with respect to y. So, x plus 2y dy, its integration with respect to y. What is the integration with respect to y? So, x is a constant here, integration of constant is x into y plus 2y integration is y square. So, x into y, 2y integration is 2 into y square by 2, that is y square, or y square derivative is 2y. So, integration of 2y is y square. This is the integration with respect to y. Now, substituting the limits, y is equal to 2x square, y is equal to 1 plus x square. So, substituting upper limit minus lower limit, you know that. So, x into, in place of y we substitute x into y is 1 plus x square, that is upper limit, minus x into the lower limit is 2x square. So, this is the first term, substitution of the limits in the first term, plus second term is y square, put y is equal to 1 plus x square, that is whole square, minus y is equal to 2x square whole square. So, 2x square whole square, then simplifying x into 1 x into x square, that is x cube, x into 2x square, that is 2x cube, plus squaring this 1 plus x square whole square, square this like a plus b whole square, 1 square 1, x square is x square whole square is x raised to 4 plus 2 times x square, minus 2x square whole square, that becomes 4 into x raised to 4. Now, this becomes the function of x. I told you already, after the integration with respect to y, then substituting limits, that becomes the function of x. Now, simplifying this, collect the like terms, x raised to 4 and minus 4 x raised to 4, that becomes minus 3 x raised to 4, and there are 2 x cube terms, x cube and minus 2x square, simplifying that, minus x cube plus 2x square as it is, plus x as it is, plus 1 as it is. So, after the simplification, you do again the integration with respect to x. So, 3 into x raised to 4 integration is x raised to 5 upon 5 minus x raised to 4 upon 4, this integration, you know that. 2 into x square is 2 into x raised to 3 upon 3 plus x integration is x square by 2 plus 1 then put the limits -1 to +1. That simplification gives 32 upon 15, that is the value of double integral bounded by the regions. So, this is what the picture of the volume, how it is generated on the region. The region is the bounded between two parabolas. You want to see more clarity of that picture, we use the GeoGebra software here to see the function, that is z is equal to x plus 2y, how it looks x plus 2y, that is what the plane region in the 3 dimension. This color graph is z is equal to x plus 2y, and below that this is the region bounded by two parabolas -1 to +1. You can see the green color, that is generated as the volume under the surface x plus 2y above the region in the xy plane. The region is here. So, that is the volume, and that pink color, that is the equation of the plane it is. Even you can zoom it, you can see the equation of the plane x plus 2y, it is a 3-dimensional plane. So, under that you can see the volume it is generated. Okay. Now, consider another example. Find the volume of the solid that lies under the paraboloid. This is the equation of the paraboloid, z is equal to x square plus y square, and above the region R in the xy plane, bounded by again the line y is equal to 2x, and one more is the parabola. The region R can be expressed as any problem. You can express the given region to be either type 2 region or type 3 region. See, I expressed in the type 2 region. So, R is equal to 0, x varies from 0 to 2. Solving these two expressions, you can do the simplification. Y is equal to x square and y is equal to 2x. These are the two curves, one is parabola, another one is straight line. Substituting one in another, so x square is equal to 2x it is. Substituting y value in another equation, x square is equal to 2x. Now, simplifying this, x into x minus 2 equal to 0. So, x square minus 2x equal to 0, x into x minus 2 equal to 0, or that implies x equal to 0 or x equal to 2. Product of these two is 0, either x 0 or x equal to 2. So, when x equal to 0, once we got x values, when x equal to 0, you can find the y values. When x equal to 0, substitute in both the equations, y is also 0. Put x equal to 0 here and here, y is 0. And when x equal to 2, and see both the equations, x equal to 2, 2 square, that is 4, here 2 into 2, 4. So, in both the equations, y value is 4. That means, those two curves intersect at 0, 0 and 2, 4. 0, 0 and 2, 4 are the points of intersection on the curves. Here, if you want to take x limits to be constants, you take 0 to 2. You want the other type of region, y range is 0 to 4. For the first type 2 region, you want to evaluate, R is the region in the xy plane where x limits are 0 to 2 and y limits already given x square and 2x, that is the boundary of y. Similarly, the same problem you can express into type 3 region. In the type 3 regions, what we have to do is, there y limits are constants. We have studied in the type 3 region, y limits are constants and x limits are functions of y. From the same expressions, y equal to x square and y equal to 2x, we can write y equal to x square as x is equal to root y. Express x in terms of y, and y is equal to 2x, writing this as x is equal to y by 2. So, what we have done is, from the given equations, we express x in terms of y, because we need x1 and x2, x limits are functions of y. So, the type 3 region becomes where y ranges from 0 to 4, already calculated the y maximum values 0 to 4 here. y equal to 0, y equal to 4, they are the constant limits, and x limits are one is y by 2, other one is root y. Now, from these type 2 region and type 3 regions, you can see the graphs here. In the type 2 region, y equal to x square is a parabola, y equal to 2x is a straight line, and x ranges from 0 to 2, it is clear, x equal to 0 to x equal to 2. The same problem in the type 3 region, the figure is same, only the limits are changed here. What are the y values here? Y equal to 0 to, you can see maximum 4, both the curve goes up to 4 here, 4 is the maximum. So, y is equal to 0 to 4, and x limits, the same equation, y is equal to 2x, I have written x is equal to 1 by 2y, the same expression, that is the lower limit of x, y by 2, and the upper limit of x is square root of y, that is y equal to x square is written as x equal to root y. So, evaluate the region either this or this. We will see both the regions here. The first type 0 to 2, it is a type 2 region, x square to 2x, x square to 2x. Then integration function is x square plus y square dy dx. So, evaluating this inner integral, that is integration with respect to y first. So, x square integration is, do it x square into y plus y square integration is y cube upon 3 dy, dy means integration of y is over, then substituting 2x and x square, that simplifies to this expression. So, after the integration with respect to y, the function becomes, it is a function of, the expression is the function of x. Then integrating this with respect to x using the limits 0 to 2, that simplifies to 216 upon 35. Similarly, the same problem if you use the type 3 region here. Type 3 region is y limits are constants here 0 to 4, y limits are 0 to 4, and x limits are functions of y, y by 2 into square root of y. Again integration, this time the integration with respect to x, dx means with respect to x first, that becomes the function of y, the integration of that becomes the function of y. Then integrating again with respect to y, that simplifies 216 upon 35. So, whatever the region, type 2 region or type 3 region, you are getting the same answers, 216 upon 35. So, what we can conclude that, hence every region R can always be expressed as either type 2 region or type 3 region. You can remember, any problem is given, we can always express either of the type 2 region or type 3 region. Now, we will consider the evaluation of, we can evaluate the integrals of type 2 regions by changing into type 3 regions. Means when you are able to evaluate both the types, so whenever the type 2 is given, we can evaluate it by using type 3 region, or to evaluate the integrals of type 3 by changing into type 2 regions. So, whatever may be the region is given, type 2 or type 3, we can easily change it to another region and then evaluate. This process is known as the changing the order of integration. Change the order of integration is nothing but one of the type is given, either type 2 is given or type 3 is given, changing them to another type, changing type 2 to type 3 or changing the type 3 to type 2. This process is known as changing the order of integration. Now, the question is why to change the order. So, in some integrals the given region is given, which may be a type 2 region or a type 3 region. It may be inconvenient to evaluate, not all the time it is convenient to evaluate, may be difficult also the given region. So, we need to change the order of integration. In such cases, when we are uncomfortable to evaluate the given region, it may be a type 2 or type 3, one may be the easier to evaluate. So, we need to change the order of integration not only changing dx dy to dy dx, that also changes the limits of integration. That is to be taken care, not simply changing dx dy as dy dx. Accordingly, you change the limits of integration. Note that the evaluation of given integral and the changed integral gives the same value. We have seen in the previous problem, whatever may be the reason, type 2 reason or type 3 reason, both are giving the same value. So, you can change any reason to any reason. Now, we will see some examples by changing the order. So, this is the given problem. Evaluate 0 to 2, 1 to e raised to x dy dx by changing the order of integration. So, what is given? First you understand what is the type it is. You can see one of the limits, they are function of x or function of y. So, in this problem one set of limits are functions of x. You can see e raised to x. So, they are the y limits. Whenever the function of x in terms of x they are given, they are the y limits. So, y limits are functions of x and x limits are constants. So, that is the type 2 region. We have studied already, it is a type 2 region. I am converting into type 3. That process is the changing the order. So, here the integration is as per this. If you want to evaluate without changing the order also you can do it. Here the integration is done first with respect to y. It is given, the y limits are given inside the integral, the y limits are given. So, integrate with respect to y from y equal to 1 to y equal to e raised to x, and then with respect to x using the outer limits 0 to 2. So, the reason of integration is I have shown in the figure here. So, 0 to 2, x limits are 0 to 2, x equal to 0 is nothing but y axis, you can easily understand, x equal to 0, and x equal to 2 is a line parallel to y axis. So, this is the boundary of the region, and y limits, y is equal to 1, it is a line parallel to x axis, y is equal to 1. Then the upper limit y is equal to e raised to x is an exponential curve, e raised to x, we plot it on the graph paper, it is an exponential curve. So, this is the given region. Now, by changing the order, the limits x equal to 0 to 2 and y equal to 1 to e raised to x, it is given as the type 2 region. These are changed to type 3, means I am converting the type 2 region to type 3. In the type 3 region, there y limits to be constants, y limits are constants. How to find y limits? So, already y is equal to 1, that is the minimum. So, y in y axis, y direction, what is the maximum value of y here? So, if we substitute x equal to 2 here in this curve, you will get e raised to 2 is the maximum here, e raised to 2. So, you can find x equal to 0 to 2, so many values of e raised to x. So, x equal to 2, that is the maximum e raised to 2. So, these are the y limits, y equal to 1 to e square, and x limits to be function of y, x limits to be function of y. From the same figure, you can express x in terms of y. So, y is equal to e raised to x. So, taking log both sides, you can find x. So, taking log both sides, log y is equal to log of e raised to x. Log of e raised to x, we know that x is equal to log y. So, this is the lower limit of x. X equal to log y is the lower limit and upper limit is 2. It is already there, x equal to 2. So, in this way, we have changed the type 2 region to type 3 region. So, evaluating that, 1 to y limits are 1 to e square and x limits are log y to 2, means the given integral, this one 0 to 2 1 to e raised to x is expressed as by changing the order in this way dx dy. Now, integrating first with respect to x here, first with respect to x, because x limits are functions of y. So, inner integral is with respect to x. So, there is no function here. So, one integration is x, integration of dx is x. Now, putting the limits log y and 2, 2 is the upper limit minus log y, put x equal to 2 and x equal to log y, that becomes the integral 1 to e square. So upper limit is 2 minus log y, that is the lower limit. So after the integration we know that that becomes the function of clearly y. Now the one more integration, that is with respect to y. So integration of 2 minus log y with respect to y. So 2 integration of 2 with respect to y, that is 2 into y. Constant integration into 1, that is 2 into y, minus what is the integration of log y? Do the integration by parts. Log y, that is y log y minus y. Integration of log y is the standard one, y into log y minus y. Then put the limits 1 to e square. Before putting, you can simplify 2y, this becomes plus 2y plus y, 3y minus y into log y. So that simplifies to 3y minus y into log y, 1 to e square. Now substitute in place of y e square and 1. So 3 into, you can see y equal to e square, 3 into e square, y is equal to e square minus y is equal to 1, 3 into 1, 3. So that is the first term substitution, minus y into log y. In this expression you substitute e square and 1. First y equal to e square into log of e square, minus y is equal to 1. So 1 into log 1. So e square into log of e square. What is the log of e square? This becomes 2. So log of e raised to 2. Log and e are the inverse functions. First you apply log, then e, that becomes the same function, or first you apply e, then log, again the same function you get. So log of e square or e raised to log 2, both are same. So log and e cancels, that becomes 2. So 2 into e square. So log 1 value you know that is 0. Simplifying to this, 3 e square minus 3, here the value of log e square is 2. So 2 into e square. So 3 e square minus 2 e square, that becomes e square minus 3. This is the value of the given integral, and even by changing the order also the same answer you get, e square minus 3. So look into another example. Given that evaluate 0 to 1 and x square to 2 minus x, x into y dy dx by changing the order of integration. Here again it is a type 2 reason, because you can see the limits, they are functions of x, they are the y limits, y is equal to x square to y is equal to 2 minus x. Here it is given where x ranges from 0 to 1 from the example 0 to 1, and y ranges from x square to 2 minus x. If you plot them in the graph paper, x equal to 0, that is a y axis, you know that, and x equal to 1 is this boundary, x equal to 1, this is the line here. Then y is equal to x square is a parabola, it is passing through the origin, y is equal to x square is a parabola, and y is equal to 2 minus x is a straight line, y equal to 2 minus x. If you are able to draw how it is the straight line, you can verify when x equal to 0, y is 2. So y value is 2, that is a maximum here, y equal to 2 when x equal to 0. X equal to 0 means y axis, y equal to 2. Here you can see what is the value of y. When x equal to 1 you substitute here, y is 1. So this is the intersection of both the curves, 1 1. When x equal to 1, y is 2 minus 1, that is 1. So the curve intersect at 1 1. Okay. Now I am going to change the problem asked is change the order, not to evaluate as it is, by changing the order and then evaluate. Now changing the order, what we have to do is consider y limits to be constants here, y limits to be constants. You can see in this picture what are the y range, y equal to 0, this is the minimum, the maximum is y is equal to 2. So they are the y limits, y equal to 0 to y equal to 2. And then what are the x limits? X limits to be function of y, x limits to be function of y. So the left boundary x equal to 0, that is the lower limit of x, and x equal to, what is the curve here, x equal to what? We cannot take x equal to 1 here. Why you cannot take? When y limits are 0 to 1 and if x limits are 0 to 1, that becomes a rectangular region. Both the limits are constants, that becomes a rectangular region. It is not the rectangular region. You see that given region is not rectangle, is bounded by two curves. So in that picture you consider x limits to be function of y. So how to find x limits? There are two curves here. If you take x equal to 0 to, in the arrow like this way, that is x equal to root y, x equal to root y. So one, if you take x equal to 0 to in this way, it is x equal to 2 minus y. So there is no curve ending, there is no curve ending at a point here. For this point it is ending with the straight line, for this point it is ending with the parabola. So there is a problem in considering the x limits to be function of y. Then what to do here? From the same figure, y limits are fixed here 0 to 2, there is no change in y limits. So x limits, it is reaching to, the lower limit is fixed x equal to 0, but the upper limit, the problem in finding the upper limit if you take in this way, that is root y, if you take in this way it is 2 minus y. We cannot take any one here because it is reaching either a straight line or a parabola. So you need to split the region into two parts here. So divide it into two parts where they are intersecting here, intersecting at 1 1 point. So y is equal to 1, you get y equal to 1, and by changing the order in this way you can split up. One region is 0 to 1, y equal to 0 to 1. We consider the half of that, half of the entire region, y equal to 0 to 1, and x equal to 0 to root y. Comfortably you can write this half region is the reaching only one curve here, x equal to 0 to root y, that is one region. The another one, y equal to 1 to 2, where y minimum is 1, the maximum is 2, and x is again, this boundary is 0, x equal to 0 to x equal to the straight line here. In previous case it was parabola, here it is straight line, x equal to 2 minus y. So there are two regions, means the given region is 1, while changing the order we are unable to find only one region. So there are two regions, so adding them, sum of the regions. So the given integral 0 to 1 x square to 2x minus 1 dx xy into dy dx is written as the sum of the two integrals. Say it is R1 first region and R2. The first region R1 is where y limits are 0 to 1 and x limits are 0 to y. In the last figure 0 to 1, x limits are 0 to parabola. Similarly, the second integral y equal to 1 to 2 and x equal to 0 to a straight line xy into dx dy. So evaluate separately this integral R1 denoted as this integral R2 and add their answers, you will get the value of this double integral. We will take one by one evaluation. The first integral R1 denoted as 0 to 1 root y xy dx dy. Here the inner integral is dx, that means integrating with respect to x. So the function is xy is integrated with respect to x. How it is? Y is a constant here, integration of x is x square by 2. So y is a constant, integration of x is x square by 2. The integration with respect to x is over. Now substituting the limits, x equal to lower limit 0, upper limit root y. So in place of x we substitute. So put x is equal to root y here, it is x square, putting that root y whole square, that is y. So y into y square by 2, this is the upper limit, minus the lower limit, substitute x equal to 0. When you substitute x equal to 0, the entire term becomes 0. That is why it is not considered here. So only y square by 2 is the simplification. Now it is a function of y. So we know that after the integration with respect to x, that becomes the function of y. Now integrate with respect to y, it is simple. Y square integration is y cube upon 3. Y square integration is y cube upon 3. 3 into 2, 6. So it becomes y raised to 3 upon 6, and substitute the limits 0 to 1. So y is equal to 1, it is 1 by 6. Lower limit y equal to 0, it is 0. So the value of the R1, the first integral, is 1 upon 6. Similarly, you consider the second integral R2. Their limits are y equal to 1 to 2 and x equal to 0 to 2 minus y, xy into dx dy. Again, the integration with respect to x is same like a previous R1 region. So y as it is, x integration is x square by 2. The only change is the limits here. X equal to 0 to 2 minus y. Put in place of x 2 minus y and 0. So putting the upper limit y as it is, in place of x you substitute. So 1 upon 2 is taken outside, that is a constant. Only it is y into x square. So y into x square, in place of x it is substituted 2 minus y. 2 minus y whole square, because x square is there, 2 minus y whole square dy. The lower limit is 0, that is why it is not considered. When x equal to 0, the lower limit becomes 0 into y, totally 0. So it is simplified to this much only. Then integrating with respect to y, it is a function of y. Before that you can simplify it, then integrate it. So y into, express this, expand this 2 minus y whole square, that is 4 plus y square minus 4y, the expansion a minus b whole square, 4 plus y square minus 4y. Now multiply by y before the integration, 4 into y, y square into y, y cube, minus 4y into y, 4y square. So that simplifies. Now integrating with respect to y. Integration of 4y. Integration of 4y is 4 into y square by 2. 4 into y square by 2 plus integration of y cube, y raised to 4 by 4, minus 4y square integration, 4 into y square integration, y cube upon 3. Now substitute 1 to 2 limits. Now putting y equal to 2 here. Y equal to 2 means 2 square, 4. 4 into 4, 16. 4 into 4, 16. 16 upon 2, 8. You can see this one. 2y square upon 2 is nothing but 2y square. Remaining two terms are same here. So in 2y square, put y equal to 2. 2 square, that is 4 into 2, 8, that is upper limit value, minus lower limit is y equal to 1, that is 2 into 1. So 8 minus 2 is the simplification of first term. Coming to second term, put y is equal to 2. 2 raised to 4 is 16. 2 raised to 4 is 16 divided by 4, that is 4, minus put the lower value y equal to 1, that is 1 by 4. So 4 minus 1 by 4 is the simplification of second term. Minus, coming to third term, 4 into 4 by 3 y cube. Put y equal to 2, 2 raised to 3, 8. 8 into 4, 32 by 3. 32 by 3 minus y is equal to 1, it is 4 by 3. Now simplify this, 8 minus 2 is 6, 4 minus 1 by 4 is 15 by 4. You can see here, minus 32 minus 4 is 28 by 3. This simplifies to 5 by 12 into 1 by 2. So finally it is 5 by 24. That is the value of the second integral. So combining those answers R1 and R2, that gives the complete solution of the given problem. So 1 by 6, it is the answer of the first region R1, and 5 by 24 is the second region. Adding them, 3 by 8 is the evaluation of the given double integral by changing the order of integration. So in this way we can evaluate any given integral. So here another example you can see from this limits. Here x limits are constants and y limits are functions of x here, minus 2 to plus 2 and y equal to 0 to y equal to 4 minus x square under root. If you remove the square root, y square equal to 4 minus x square, that is nothing but a circle. X square plus y square is equal to 4 is a circle. Circle radius is 2, center at the origin. So, this is a semicircle, minus 2 to plus 2. Here y limit is 0, that is the x axis. It is the half of the circle. Now, by changing the order, change y limits to be constant here. So, y boundary is y equal to 0 to y equal to 2, that is the limit here. Y limits are constants, and x limits from left hand side to right hand side along the x axis. You consider this side, it is square root of, simplifying that, square root of 4 minus y square, we take minus sign here left side, and the same equation plus of square root of 4 minus y square. So, they are the x limits. Then the function is same, evaluate first with respect to x, then with respect to y, it is giving the same answer. See one more example with the infinite limits given here. From the given limits, you can easily identify what is the type is given here. This is the type 2 again, x is present in the limits. So, y limits are x and infinity, they are functions of x, y equal to x to y equal to infinity, and x limits are constants 0 to infinity. So, here the reason you can plot here. So, y is equal to x is a straight line exactly middle of the first quadrant, y is equal to x, and y equal to infinity. Infinity you cannot plot here, the entire plane it is first quadrant you get above the entire first quadrant it is. When x limits are 0 to infinity, if you extend it to infinite axis, and y is equal to x up to infinity and y equal to infinity up to infinity along y direction also. So, the first quadrant you divide that, that is the reason. The reason is half of the first quadrant it is. The entire first quadrant 0 to infinity, its half portion is the given reason here, y is equal to x to y equal to infinity. It is not only this much as shown in the figure here. If you extend to infinity, this line is not the infinity here, this line is not the infinity. So, it is extended to infinity. Here also it is not the boundary, it is extended to infinity. So, entire first quadrant is divided into two parts. The above the line y is equal to x is the region R. Now, changing the limits of integration. The given limits are x equal to 0 to infinity and y equal to x to infinity. So, x limits are constants here. So, it changed to y limits to be constants here. See the y boundary, y equal to 0, that is x axis, and y equal to infinity. I told you infinite region it is infinity, they are the y limits, and x limits are x equal to 0, this boundary, that is y axis, then line 0 to this line, that is x equal to y. So, x equal to 0 to x equal to y, they are the x limits. So, it is written the change limits are 0 to infinity and 0 to y. The function is same. So, evaluation becomes 1. So, in this way we can change any type to any type. Now, moving to the another concept, change of variables in double integrals. So, in many cases the evaluation of double integrals becomes easy when there is a change of variables. So, in some regions we are unable to, means not comfortable to evaluate the double integrals. If we change them into another variables, that becomes comfortable to evaluate. Let R be the region in the xy plane, for example. Let xy be the Cartesian coordinates of any point P in the region R. Let we introduce two new variables, u and v are the new variables in another region R star, such that there is a connection between the xy and uv, such that xy and uv are connected through the equations. X is a function of u and v and y also function of u and v. Then the double integral in the variables x and y can be transformed to the double integrals in the new variables. The given double integral in the variables x and y can be transformed to the double integrals in the new variables x and y as follows. See that the given double integral is this double integral over the region R fxy dx dy, it is given. Now changing to the new variables where x and y they are functions of u and v. So, you will get a new function, they are function of u v. Then dx dy, this is important, dx dy is replaced by mod of j du dv. So, where j is your Jacobian of xy with respect to uv, you know how to find the Jacobian value from the equations. When x is a function of u and v, y also function of u and v, you know that the Jacobian definition dou xy upon dou uv, that is the 2 by 2 determinant, dou x by dou u, dou x by dou v, second row y with respect to u, y with respect to v, that gives the j value. So, that is substituted in the changed integral. Function of uv dx dy is replaced by du into dv. There is a particular case changing Cartesian to polar coordinates. Now, the Cartesian variables x and y are changed to polar coordinates r and theta. You know already familiar with r and theta are the variables connected to polar coordinates. Through the equations, you know the equations. What are the equations connecting the Cartesian to polar coordinates, which are x is equal to r cos theta, y is equal to r sin theta. So, these are the equations connected to Cartesian to polar coordinates. We can vice versa, we can express r and theta in terms of x y also, means squaring both the equations x square plus y square, you will get r square. R is nothing but a square root of x square y square. You can also write what is theta in terms of x y. Now, the Jacobian in this case, you are already familiar in partial differentiation. J is Jacobian of x y with respect to r and theta. So, dou x by dou r, dou x by dou theta, dou y by dou r, dou y by dou theta. Then the determinant value gives r, that also you studied in the previous semester. So, the double integral over the region r fxy dx dy is reduced to f of r theta, that becomes the function of r and theta. So, dx dy is replaced by r dr d theta. Now, why to change to polar coordinates? You can ask the question, why is it necessary to change to polar coordinates? So, to evaluate the double integrals over any region r fxy dx dy, where r is one of the following type of regions. You can see the pictures. They are, the region may be a circle or a part of the circle. Region is a circular region or may be the part of the circular region, or may be between the two circles to evaluate the integral between one circle to another circles. So, here the r in terms of Cartesian coordinates is complicated. You want to express in terms of the limits may be complicated, but the same region can be easily described using polar coordinates. That is important. This is the reason we can easily describe in polar coordinates for such regions, not for all the regions. Whenever the region is a circular or part of a circular region, may be between the two circles. In such cases, it is easy to describe using polar coordinates. And what is dx dy in polar coordinate? This is important. We told you already dx dy is replaced by r dr d theta, but dx dy is in the rectangular coordinates, it is the length into breadth, area of a rectangle dx dy. So, what is that in the polar coordinates? What indicates dr d theta into r? So, the rectangular grid is constructed from the vertical and horizontal lines. You know that from x equal to a to x equal to b and y equal to c to y equal to d, you will get a rectangular grid there. In polar coordinates, r equal to a stands for, it is a circle, r equal to a, like x equal to a and x equal to b are the lines, straight lines. Here r equal to a, r is what? It is square root of x square plus y square, means you express polar into Cartesian. express polar in terms of Cartesian. So, r square is equal to x square plus y square. R is equal to a means root x square plus y square equal to a. That means x square plus y square is equal to a. Which is that? It is a circle. R equal to a is a circle of radius a centered at the origin. So, in polar coordinates, to draw a circle x square plus y square equal to a square is it is denoted as r is equal to a. A stands for the radius of the circle, its center is a, and theta is equal to alpha is the angle. Ray, you can say it is an array. It is emanated from the origin with the x axis. So, the polar grid is built out from these circles and rays. So, the Cartesian is converted to r dr d theta. You can see here what I told you. Theta is equal to alpha is a ray making an angle with x axis, and theta equal to b is another angle with the x axis, and r equal to a is a circle. You can see the part of the circle is drawn here, r equal to a, and r equal to b is another circle. So, you can see the region bounded by two circles with the angles theta equal to alpha, theta equal to beta. That is discretized in the Riemann sum. I told you in the beginning session, dividing them into n number of sub regions. It is not a rectangular region. So, dividing them you will get the smaller region. So, r is this is theta angle, and that radius is r. This is another theta. It is the difference you can get delta theta. Theta equal to alpha and theta equal to another angle. The difference is taken alpha if it is beta, beta minus alpha is delta theta. The difference in theta, that is delta theta. Similarly, r is equal to a and r is equal to another number, change in r, that difference is taken as delta r. So, in dx dy, dx is the difference in x direction, dy is the difference in y direction, that is taken as here dr, difference in r. So, product, the area of that small region is r dr into d theta. That is why dx dy is r dr into d theta. You can demonstrate even using the graph also how the dx dy is changed to dr d theta. See, this is the rectangular region dx dy. So, I have covered up to 2 pi here. Dx dy in the Cartesian, this is the polarities r dr d theta. So, the element every dx dy in Riemann sum we have seen. This is the small rectangle. We have divided the xy region, the rectangular region, into n number of this one. You can see the corresponding, this one dx dy corresponds to r dr d theta, small region. You can see anywhere. See that this dx dy corresponds to this dx dy corresponds to so this is constructed using GeoGebra dx dy. Okay. So, it is understood that the rectangular region, that is Cartesian region dx dy, in polar it is replaced by r into dr d theta. So, each sub region, they are the areas in the polar coordinates, r into dr d theta. Each, all those are added according to Riemann sum, you will get the total area in the polar coordinates. So, that is the small area. Like that, adding all those areas, you will get the dA meanings. Okay, this concludes about the how the conversion of Cartesian to polar, that is the change of variables. So, in the next session, we will go to the examples, how to solve them using the polar coordinates. Thank you.